Yeah, today I'm very happy to invite my friend Dr. Arun Nayak from Reactor Technology Division, Head Reactor Technology Division. In fact, walking back home from Vandigraph to the colony, we used to discuss very passionately. In fact, he used to talk very passionately about what India should do, what VRC should do on reactor technologies and all that. I'm very sure what he's going to talk in today's talk, that is relevance of small modular reactors for a decarbon energy sector for India, especially in these times of climate change and all that. And I think recently he has also initiated some of the implementing some of these programs. I'm very happy to invite him. I would like Dr. Dureja to introduce the speaker, Dr. Arun Nayak, Professor Arun Nayak, I should say here. Please introduce.
Yeah. Good evening to all of you. Welcome to this HBNI colloquium on relevance of a small modular reactor for a decarbon energy sector, which will be taken up by Dr. Arun Kumar Nayak. A brief introduction about him. Dr. Arun Kumar Nayak is a graduate in mechanical engineering from NIT Rourkela in 1987 and postgraduate in mechanical engineering from NIT Warangal in 1989. He joined the Reactor Design and Development Group in BRC in 1990 after completing 1-year orientation course in nuclear engineering from 33rd batch of BRC Training School. He did his PhD in nuclear engineering from Tokyo Institute of Technology, Japan in 2000 and worked as a postdoc fellow in Interfaculty Reactor Institute, Technical University of Delft, the Netherlands in year 2002-2003 and in Nuclear Power Safety Division, Royal Institute of Technology, Sweden in year 2003-04. He also worked in Institute of Nuclear Energy, Stuttgart University, Germany under DST DAT project in the year 2007 to 2009. He has made seminal contributions to several domain areas of Indian nuclear power program. He played key role in design of SWR with several innovative first-of-a-kind passive safety systems and built many world-class experimental facilities to establish their design margins. To address reliability of these passive systems, he developed a novel technology, Apsara, which is acclaimed worldwide. He was consultant to IAE for several years for resolving key design issues of passive safety systems deployed in advanced reactors. He is internationally known for managing core melt accidents in nuclear reactors. The core catcher design of SWR is one of his significant contributions both with regard to technology and science. Under his leadership, very challenging high temperature experiments with prototypic core melt for establishing core catcher design was conducted. First time in world, he has conducted several experiments with molten corium simulants in model of 700 megawatt PSWR Calandria and demonstrated the capability of vault water to cool and retain corium in the Calandria vessel with adequate safety margins. He demonstrated that currently operating water-cooled reactors can have enhanced safety margin if operated with nanofluids. Suppression of flow instabilities, enhancement in natural circulation flow, and CHF, reduction of condensation, induced water hammer, and brightest examples of his innovations. Under his leadership, BRC has built a 20 kilowatt solar thermal plant with superheated steam production at 225 degrees centigrade. Currently, he is working on development of an innovative small modular reactor, which is inherently safe, passive by design, factory built and shipped to site for direct installation, and have the potential to build them in vacated sites of coal-based thermal power plants. He has been actively involved with HBNI for teaching and guiding MTech and PhD students. He is Associate Editor of ASME Journal of Nuclear Engineering and Radiation Science and Journal of Computational Thermal Science. He is recipient of several awards, which include Homi Bhabha Science and Technology Award. He has written 4 books and published more than 500 research papers in academic journals and conferences. Presently, he is heading Reactor Technology Division of BRC and is Senior Professor at Homi Bhabha National Institute. He is Fellow of Indian National Academy of Engineering and Maharashtra Academy of Science. So, welcome you, sir. You may take over, sir.
First of all, I'm grateful to HBNI Dr. Grover, Dr. Ravi Saab, for inviting me to give a talk in SBNI, especially in the SBNI series of colloquium on this important topic of small modular reactors, because he was knowing that I work in this field. So thanks a lot to Ravi Saab and also Dr. Dureja for kindly introducing me to this audience. The topic on which I am going to speak is a very, very important topic, very timely, looking at the global energy sector transition and its relevance to India, of course. The decarbon of the energy sector, we all have been hearing for quite some time, especially in the last decade, you can say. The last decade is very important also from nuclear point of view, especially after the Fukushima accident. There was really a big dilemma, there was a big concern worldwide that whether nuclear reactors or nuclear technology at all to be pursued considering the safety issues. But at the same time, there was, I would say that very big thrust that the energy sector need to be decarbonized. So looking at one front, we don't have to go ahead with nuclear because of the safety crisis. But at the same time, to decarbon the full energy sector, again, there is a revisit of nuclear technology. So considering both contradictory aspects, now the small modular reactors, what I felt I'm going to present here, probably would play a major role in the decarbon energy sector. And that's what I'm going to present here. So the talk is going to be divided into two parts. The first half, what I'm going to speak about, the importance of decarbon the energy sector, which I will speak roughly in the next 30 minutes or so. And the other 30 minutes, I'm going to speak about how small modular reactors are important in a decarbon energy sector, particularly, especially looking at India. So with this background, I want to, Okay, with this small background, let us move to my first slide. I hope it is all visible to all the audience and my words also they are able to hear. Look at the current energy scenario in India. I start with this. You may probably, the numbers, I will say that don't be very critical with the numbers, but the numbers also are very important. So today, what is the total primary energy supply in India is roughly, I'll say, close to 900 million tons of oil equivalent. It's a huge number, which I'm going to show you after 2 or 3 slides. And if you see that where we get this 900 million tons of oil equivalent, they're primarily from carbon-based sources. The coal contributes roughly 44%. Oil is 25%, biomass 13%, natural gas 6%, or roughly more than 90% of them comes from carbon-based sources. The renewables and other contributions are very small. And it is not only the case in India, but mostly it is also the world average. The numbers are very typical to this. And let's look at what we do, how much we have, what nature has given us, that is what we have, and how much we import. And as we all know, oil is the most critical aspect because 2/3 of this energy source, especially from oil, we import. Coal is also almost 1/3 we import. Natural gas almost 50 and 50%. So quite a significant of the total primary energy sources are imported, and that is basically what Kakodkar Saab used to say is an important element on the health of our economics. Our country, because more than 50% of the total energy is imported, so it bears a big burden on the tax system. Then how do we consume that? Let's look at how do you consume. So 900 million tons of oil equivalent is imported. When you convert to usable energy form, roughly 600 to 650 million tons of oil equivalent is what we consume after the losses. And out of that, today, especially for India, the industry is one of the largest consumer. Almost 40% of energy is consumed by industry, both for heat as well as for electricity purposes, followed by the residential. Almost 30% of that is consumed. Again, mostly for electricity as well as for cooking, that is for heating purposes. Transport comes the next, almost close to 16%, which is roughly 100 million tons of oil equivalent goes for transport sector. And the rest all, very small, I will say 13% goes in the services sector. So this slide is very popular and which we have been seeing from a lot of presentations. But before we go to the bottommost slide, look at the top rightmost slide, the total primary energy consumption. We are not small. We are the third largest consumer in the world, apart from China and the United States. China leads, followed by United States, and third is India. So far, the total primary energy consumption is concerned, we are the third largest in the world. But fortunately or unfortunately, this is what lives. Let us leave it for time being. Because we have a large population, roughly like 1.4 billion, so our per capita energy consumption is quite poor. Today, we consume something like 1208 kilowatt hour per year, which Dr. Grover Saab has been saying. Look at our neighbors, they consume much more than us, more than 2 times, 3 times. The world average is almost 3 times what we consume. And the OECD countries, they consume more than 7 times what we have. So then there is a big difference that what we have and what we have to target is whether we should target 3 times, 5 times, because this per capita energy consumption, they are so closely linked to the Human Development Index. Today, if you look at the bottommost graph, I don't know whether you are able to see the cursor. So India is not so well placed, and we have to climb somewhere towards the top, having an HDI of 0.9 or 0.8 at least. And that way, the per capita energy consumption has to multiply by several times. This is one front. But where the energy demand is coming from? The Niti Aayog says India houses today roughly 100 million people without access to electricity and more than 840 million people without access to clean cooking fuels. And if you look at our installed electricity capacity, this has really jumped quite fast from 116 gigawatt to 377 gigawatt in the last 10 years, with a compound, if you see the annual growth rate of more than 8.42%, is significant. And significant if you compare with that in the world. And this is primarily driven by our economic growth, which is one of the fastest in the world. But there is a problem with our population. The Population Reference Bureau has estimated Indian population to reach something like 1.67 billion by 2050, surpassing that of China. And similar estimates also have been made by UN to have around 1.64 billion by around 2050. That means another, I will say 20 to 30 crores people are going to join us in the next 20 to 30 years. Please remember, another 30 crore people are going to join us in next 3 decades. And what is the implication? Implication is written in the next line that India will soon become the world's most populous country, adding equivalent the size of a city like Los Angeles, population of Los Angeles, to its urban population each year. And this population is going to demand another 25% energy by 2040. And to meet the electricity demand over the next 20 years, India will need to add a power system of the size of a European Union to what it has now. Because India's population, especially if you look at the urban sector, is going to increase from 31 to 51%. This is what is projected. So there is going to be significant energy demand, especially in the urban sector. And the GDP is also going to grow from 8.5% in 2012 and is going to be steady till 2047. And there will be also going to be higher energy demand in the manufacturing sector, which is expected to rise to 34% in 2047 from 16% in 2012. Also, we have very ambitious plan in energy sector, provide continuous uninterrupted power supply to every household, housing for all, creation of several smart cities, 10% reduction of oil and gas import dependency by 22, and so on and so on. And last but one is the provision of clean cooking fuels, which the IPCC, the International Panel for Climate Change, especially targeted to Indian, especially rural India, to ban the bad cooking fuels, especially from cow dung. Now, the most difficult part is in this graph. How much energy really we require by 2050? To me, it is one of the most difficult jobs. You'll look at the top red line shows how your population is going to rise steadily till 2050. After that, probably it will going to be remain stable or controlled, or it may dip down also slightly. But let us look at till 2050 or a little bit to till 2070. If you look at the bottommost graph, from 2005 till 2020, this is how we have been consuming the energy, something like little below 5,000 terawatt hour to roughly 9,000 terawatt hour in the last 15 years. Almost it has doubled in the last 15 years. Assuming we grow in the same way, by 2050, this is one of the poorest model, I will say, we can reach something like 20,000 terawatt hour. So today in 2020, we are below 10,000 terawatt hour, and 2050, assuming we move in the same straight line, probably will reach or we require 20,000 terawatt hour, which most of the experts in the audience will not accept because we are targeting to have a HDI close to that of the European Union or the Western world. Others may speak, no, we have to grow several times at least to that of 50,000 terawatt hour, at least 5 times what we have today. That means we need to grow at least 5 times of today to reach 50,000 terawatt hour, or at least 2 times of today, if what I say business as usual model, move in the same slope. So these two numbers which I speak, 20,000 terawatt hour by 2050, or in a very ambitious way, 50,000 terawatt hour per annum by 2050. Please keep in mind these two numbers when I go to my next slides. So as I said that in 2020, we consume nearly 9,032 terawatt hour energy. BOW model, I said that 20,000 terawatt hour, which is roughly 2 times of today's consumption we need to achieve. And with the aggressive model, assuming we are so aggressive, we want to reach to have a life closer to that of the Western life, 5 times we need to produce. So if I look at the difference, it's a huge energy deficit of really, at least I would say 10 to 40,000 terawatt hour, and which must be achieved in the next 30 years. And the biggest story, even with 10,000 terawatt hour, let's look at what is the biggest story. The biggest story worldwide, including that of India, is the greenhouse gas emissions, because as I said from my second slide, almost more than 90% of the fuel that we consume are basically linked with the fossil-based fuels. And today, the carbon-based oxides, which includes the carbon monoxide and carbon dioxide, they're the root cause of the greenhouse gas emissions. Almost 76% of GHG is emitted from carbon-based sources because of CO2 and carbon monoxide. Another 16% is from the methane, which comes from biomass and waste. Nitrogen oxide also is almost 6%, and the fluorine-based gases, they emit 2%. Historically, if you look at from 1990 to 2020, roughly, or I'll say in the last 30 years, you look at how much greenhouse gases we have added to the atmosphere. Believe it or not, we have added very significantly from roughly 40 gigatons of CO2 equivalent in 1990 to almost 60 gigatons CO2 equivalent in 2020. Roughly, you can say, for almost 50% increase in the last 30 years has happened. And whatever happened is the history I have told you because of the type of the fuel we consumed. And similar things has happened not only from the carbon-based sources, but also from methane, nitrous oxide, the fluorine-based gases. You see, proportionately they have increased. It's just not just CO2 or carbon monoxide alone. And let's compare who has emitted how much. The China is today the largest emitter, almost 10 billion tons they emit, followed by United States and India. The Russia follows. When you compare, of course, the per capita energy, per capita CO2 emission, probably we are one of the lowest, maybe amongst these countries, even as compared to Russia or Brazil. But because our population is large, so we have also emitting large that's amount as compared to China or even United States also. So this is something you look at, that China is almost emitting 10 billion tons, followed by United States, and India roughly emits 3.5 billion tons of CO2 per year. And if you look at the sectors which emits how much, the coal, oil, and gas, they are the prime drivers of those CO2 emissions. The coal, oil, and gas, they amount more than 70 to 80% of the total, CO2 emissions, followed by cement and net land use. And that, if you see historically, from 1850 to 2020, especially after the industrialization happened, these components started steadily rising, and today they have expanded very significantly, especially if you look at beyond 1950, it has significantly increased. Similar behavior is that of India. We have also steadily put the CO2 emissions exponentially. They have been rising for the power industry, which is one of the largest, followed by the industrial combustion, and the transport sectors, non-combustion sectors also emit quite a significant amount, followed by the last, but not the least, is coming from the residential sectors. This is one of the very important slides I wanted to share with you because of a very recent, I'll say that this year's Nobel laureate, the physicist Shigeru Manabe, for his excellent work, which happened many, many years back, how much the world or the earth gets heated because of the greenhouse gas emission, especially because of the carbon dioxide emission. Many years back, he had calculated and predicted that if the CO2 concentration increases by 2 times in the environment, the temperature of the earth is going to increase by 2.28 degrees Celsius, and almost equal amount is going to cool down if the CO2 concentration in the environment reduces. A very, very important thing. Initially, people were not believing that carbon dioxide is the root cause for the temperature rise, but now it has been well known, and this number is very, very important. If the concentration increases by 2 times, the environment temperature increases by more than 2 degrees Celsius. Let us record this number right now in mind. And how much we have climbed in the CO2 concentration in the historically, if you see. From 1750, I will say, until 1930 or 90, or you look at 1900, the change in the CO2 concentration was negligible small. And beyond 1900, I'll say, the CO2 kept on climbing is all because of significantly the large industrialization, the growth in transport sector, and our, I will say that, a hunger for energy. These are the reasons why the concentration kept on rising. And how much it has increased, if you look at the leftmost, I will say that axis, it has gone from 280 ppm and it has climbed more than 400 ppm, almost 50% it has already climbed. And because of the amount of CO2 which has jumped from 5 gigaton CO2 roughly in 1750, and today it is almost 30 gigaton CO2 which we have pushed into the atmosphere. And this 2 degrees Celsius, which I showed 2 slides back, is a very, very important bearing with regard to the atmosphere, health of the atmosphere, health of the environment, health of the earth. Why? Why should we limit below 2 degrees Celsius? If we double the amount of CO2 in the atmosphere over the pre-industrial level, the earth would warm up more than 2 degrees Celsius. This is what I showed you 2 slides back. And some scientists, they predict it can warm up between 1.5 to 4.5 degrees Celsius. The biggest question is how much warming humans can tolerate. It's really very, very complex and a highly non-linear bioscience. Nobody has an answer today that how much we can safely tolerate. But the 2 degrees Celsius was endorsed by a council of German scientists who were advisors to Angela Merkel when she was the environmental minister at that time. They are thinking that human civilization had developed in a period when sea levels remained stable and agriculture could flourish. Staying within that bound and preventing global average temperatures from rising more than 2 degrees Celsius seemed like a reasonable rule of the thumb. But the critics did not accept. They grumbled on 2 degrees Celsius, saying that these are arbitrary. But later on, I'll show you also a couple of slides where scientists could produce enough evidence that above 2 degrees Celsius, there is a rapid sea level rise, risk of crop failure, and coral reefs can collapse. By 2009, almost every government has now endorsed the 2 degrees Celsius limit. This is what the IPCC 2021 report says. It's yet to be published, but it has shown now several, I think, papers they have reviewed and find out that concentration of CO2 has reached an unmatched level 400 ppm. It has exceeded as compared to 2 million years ago. This is first thing. And it has any implications both with regard to the glacial retreat as well as the rise in sea level, which is faster than any prior century for 3,000 years. And the last decade, we all have, I think, experienced a relatively warmer than any period for 125,000 years. And so on and so forth. The last one is the worst. That ocean acidification is one of the highest level as compared to last 26,000 years. So how much warming is still we can bear? Suppose we keep on adding the carbon dioxide. The 3 scenarios the IPCC report has, they have found it out. One is go with low emissions, which let us say the global temperature, we go to 1.4 degrees Celsius. We continue with the high emissions, where we go to 4.4 degrees Celsius. So that is relatively 3 times more than we are worsening our environment conditions. And that will cause an implications, especially on the precipitation, which can be 3 times or 3.5 times worse, from 2.4% to 8.3%. The global mean sea rise level can be 2 times worse, from 0.38 meter to 0.77 meter. And the last is the worst one. That is the Arctic sea ice, which can reduce by 8 times, from 2.4 10 raised to 6 kilometers square to roughly 3 into 10 raised to 5 kilometers square. then what is your CO2 budget? This is also very, very important. If we want to limit to 1.5 degrees Celsius with a 50 to 67% probability, our carbon budget is 400 to 500 gigatons. Suppose we have to limit at 2 degrees Celsius, that is between 50 to 67% probability, our carbon budget is between 1150 to 1350 gigatons. And today we know by 2020, we have added already 40 gigaton of CO2 per year. So to reach 400 tons, it is just 10 years from now. To reach 1200 gigatons, it is just 3 decades from now. So the rule of the thumb is that how do we want to proceed? So the implication is that if we want to reduce the Earth's temperature below 2 degrees Celsius, we need to have a drastic cut, a drastic emission cut to reach below 1.5 degrees Celsius limit. So that is what we have to keep in mind. So it is not that we have sensitized ourselves. The world is working. The world is highly sensitized. There are a lot of international efforts to reduce the greenhouse gas emissions. And it has been now well recognized that deep decarbonization is an important aspect to is important aspect in the, I would say, energy sector to reduce the CO2 emissions. For example, in 2010, the US electricity generation was something like producing 500 grams of CO2 per unit of electricity per kilowatt hour. And to achieve the 2050 target and whatever is set by the Paris Agreement, they need to reduce by 97% of that. That is to less than 15 grams CO2 per unit. That means from 500 to 15. And the recent study by MIT researchers suggests that 15 grams CO2 per unit is still very high. They need to reduce below 1 gram CO2 per unit. The IPCC, in a very recent report, recommends complete decarbon of the energy sector, including transport, building, cooking, infrastructure, industry. Almost in every sector, it has to be completely decarbonized to reduce the greenhouse gas emissions to meet, if we want to really meet the 1.5 degrees Celsius constraint. So what the United States, China, UK, and France have to target? 2017, if you look at the leftmost column, per unit, how much CO2 they emit is quite high. And the 2050 IEA target, suppose 2 degrees Celsius scenario we have to maintain, the US has to limit to 11 grams CO2 per unit, China 24 grams CO2 per unit, UK 11, France 11, and the MIT says no, 11, 24 is too high. They have to complete decarbon the energy sector, which is almost 1 gram CO2 per unit. India, we have made very serious commitments in Paris. And these numbers, what I'm going to read, are basically our India's NDCs with regard to Paris Agreement. That is to reduce the emission intensity of GDP by 33 to 35% of 2005 levels by 2030, 40% fossil-free power generation by 2030, creation of additional carbon sink of 2.5 to 3 billion tons of CO2 equivalent. And it is a huge number, really, if you look at whatever I'm reading here. And to achieve that, suppose we target today, especially if I go by a business as usual model, reducing CO2 emissions by 35%, we have to reduce from 612 million CO2, which we were emitting in 2005, to 397 million tons of CO2 in terms of absolute emissions. And that will restrict the coal power to less than 300 terawatt hour per annum. Now, suppose we target what the number 15 grams CO2 per kilowatt hour, then our coal will be much, much smaller. It will be hardly 25 terawatt hour per annum. The COP26, the 5 nectar or Panchamrit points which we committed, the India will reach non-fossil, did not say green, non-fossil energy capacity of 500 gigawatt by 2030, meet 50% of its energy requirements from renewable energy by 2020, and will reduce total projected carbon emissions by 1 billion tons from now onwards till 2030. By 2030, we will reduce the carbon intensity of our economy by less than 45%. By 2070, we will be net zero. This is what we have committed in COP26. But what is net zero? I think most of the experts must be knowing, but to a general audience, what is net zero? Net zero means whatever we are emitting, that we have to take it back. It's similar to like a water tank. Whatever amount of water we are pushing in, we have to take it back so that there is no net accumulation of water in the tank. Almost similar thing. And in Paris Agreement, suppose we have to limit to oil below 2 degrees Celsius or 1.5 degrees Celsius to commit that, and it is well recognized that we have to take out so much of CO2 which we have added, we have to take it away. In addition, we don't have to add anything more. That is the meaning of the net zero. The International Energy recommends to have or to achieve net zero, what we have to do. We have to reduce CO2 to net zero by having 500 million tons of low carbon hydrogen, especially for the transport and industry. The transport and industry have to do away completely from oil, gas, and coal. So 520 million tons of low carbon hydrogen has to be produced, especially to meet the net zero condition. Then almost 85% buildings have to have zero carbon. 70% electricity globally has to be from solar, PV, and wind. Renewables are almost 90% of the total electricity generation. 90% of heavy industry have to consume low carbon energy, and 7.6 gigaton of CO2 have to be captured. This is a very, very big numbers and very, very critical approach if we have to achieve the net zero. And how it reflects in the energy sector. Look at, today we produce so much of energy, but not in the electrical form, which is used in the most of the like industry, transport, partly in the residential sector, and also largely in agriculture and commercial sectors. What is projected from this is that the agriculture, the commercial, residential sector have to be almost 100% run by electrical form of energy. The industry and transport can run partly from electricity and partly from hydrogen. Especially the transport sector, we can say that 60% of the total energy can come from electricity and 40% maybe from hydrogen. And industry can be the reverse, maybe 30 to 40% from hydrogen, from electricity, and the rest all come from hydrogen. But where hydrogen will come from, that is a big question. Hydrogen will come from, again, from electrolysis, and that also requires electricity. Or by high temperature splitting of water, which is can come again from the heat produced from carbon-free energy. So the green hydrogen, which is being talked about here, is also today, if we target, has to again come from electricity. That means the full energy sector has to be obtained from electrical energy. So what risk and opportunity we have? Risk comes because if you don't target to decarbon the energy sector for India, it is estimated that there is a loss of more than 7.14 lakh crores per year. Because of floods, there will be emerging regulation on emission caps and so on and so forth. But there are opportunities which is projected that we can have something like 3 lakh crore we can earn also. How? That I will be speaking in some of the slides afterwards. But before that, again, I'm bringing out the biggest dilemma in the energy transition, that how much carbon-free electricity this country can produce. This itself is a big question, because today, 2021, total installed capacity in the country is roughly close to 400 gigawatt, which is around 1381 terawatt hour per annum. It's a very small number, almost 1400 terawatt hour per annum, which is roughly 15% of the total energy that we produce, with an average plant load factor of 53%. And I am saying that if we go with the current growth rate, we have to target 10,000 terawatt hour per annum electricity by 2050. Or if we go by aggressive model, I'm saying that 50,000 terawatt hour per annum, which is 7 times or 17 times from today's electricity generation. Whether by 2050, our systems, all the systems that I spoke about, they run by electricity completely, or electricity and hydrogen produced again from electricity or high temperature splitting, maybe roughly I'm just saying, that is a huge number we have to jump 7 times to 17 times from whatever we have produced. On the other hand, suppose we keep on growing before 2050, in the same way that we are moving till 2020, especially in the electrical sector, our estimate is that by 2050, we might produce 10,000 terawatt hour with all carbon-based energy sources, which is not acceptable. There is a big thinking that in this mid-journey to net zero, let us use coal, because it otherwise is a big burden also on the economy. Let us continue with coal, with clean coal technology, carbon capture and storage, till we reach the net zero. But what is the implication? The implication is also serious. With carbon capture and storage, it is now, I think, estimated efficiency of the power plant is reduced, and the cost of the electricity production is likely to go up by 45 to 50%, and who is going to bear? The consumer, due to the increase in fuel cost and capital expenditure. And also by 2050, for example, if you go ahead with the same rate, what I showed in the previous slide, till we reach the net zero with the coal-based technology, we are going to add something like 7,800 million tons of CO2 to the atmosphere. So this is another big concern. So what is the option? Option definitely is the renewable sources. So we have to look at renewable sources and look at whether we can accomplish whatever is such a huge deficit. But what is the maximum potential solar of India? How much God has given us? MNRE projects that 1640 terawatt hour per annum, assuming 3% of the wasteland is covered by solar PV. Niti Aayog says 2040 terawatt hour per annum with all storage technology available and smart grids in place. Professor Sukhatme has postulated for 3 conditions: 5%, 10%, 15% to be covered by of the barren and uncultivated land to be covered by the solar PV, and it can produce something like 2,190 terawatt hour per annum to something like 3,080 to 3,285 terawatt hour per annum. With the 25% annual plant load factor, considering availability of solar energy for 8 hours per day and 9 months per year for Indian context. Suppose we assume by 2050, full storage technology is deployed. There are no plant outages and no losses, and assuming 10% of the barren land has been utilized, our calculation is that maximum we can produce 2,000 terawatt hour per annum. And then we sum up whatever MNRE is spoken about, wind, hydro, bio, and that of the solar. Together we can produce 3,826 terawatt hour per annum. So today in 2022, we have 151.39 gigawatt electric installed capacity from renewable, which accounts roughly 38.5% of total electricity generation. But with low availability of renewable energy sources, the installed capacity should be multiplied by many folds supposed to reach the country's requirements. The major issue with renewables, we all know, they're intermittent. They're not available whenever there is a demand. You go from winter to summer, the demand changes. Day, night, the demand changes. And wherever the demand, probably it is not there. And the poor capacity factor is because of that, it's around 20 to 30%, depending on whether it's wind or solar. Life of the plant, today's technology is small, needs replacement very periodically, huge waste generation and management required. Suppose we target such a huge 10,000, 20,000, I don't know, today it is 4,000 is maximum that we can get. And the employment opportunity, the last point, is very, very critical. Today, India's employment is largely in carbon-based sources, which include oil, gas, and the thermal power plants. Probably they are one of the largest employment sources in India. And tomorrow, if they are closed, vis-a-vis what employment we generate in these renewable sources is a big question. What fraction of the people we can create employment for them? The base load is another very important factor. The base load means what we can continuously supply to the grid even though the load changes. It should be available. It's almost available 24 hours a day, all year around. The nuclear, coal, gas, hydro, they are well known. They are available with a high capacity factor. On the other hand, the wind, solar, they are fluctuating and they can be used as a load sharing and not as the base load. It's well known. Then why nuclear energy? High capacity factor today is as good as 90% as compared to solar 20%. The land utilization, if you look at nuclear, because of the high energy density, we can produce 1 megawatt electricity in less than an acre compared to renewables, something like 7 to 10 acres. Life is 60 years as on today's technology, renewables 20 to 25 years. Nuclear proven technology, more than 60 years of experience exists. Hence, nuclear energy has to be considered as an important element in the energy mix, especially to address the base load. A right side table I have given a good example. Suppose we have a 100 megawatt electric plant operating 24 hours. They can produce maximum 2,400 megawatt hour energy. Nuclear power produces 2,167. Coal produces 1531 megawatt hour. Natural gas 1020 megawatt hour. Hydroelectric 955 megawatt hour. Concentric solar 792 megawatt hour. Wind 480 to 960 megawatt hour. And solar PV is 360 to 450 megawatt hour. So if you look at, I build a 100 megawatt plant, from solar PV in 24 hours, I can sell energy hardly 400 megawatt hour. But nuclear, I am selling energy almost 5 times of that. The other aspect is how much gram of CO2 it emits per kilowatt hour. We all know coal, biomass, natural gas, they are very, very high emitters. But as compared to solar, wind and all, nuclear is also an excellent, I will say that, clean energy source. So by looking at all these slides, it's very important that we have to augment the nuclear generation capacity in the non-carbon energy sector by several fold. It is very, very important. And the opportunity exists, especially look at the first plate, because suppose we go for non-carbon energy sector, large number of coal-fired plants will be retiring. We need to replace them, especially to provide a base load when the coal is not available. And then there is a demand, there will be much demand for green hydrogen for transport and industry. Let's look at how nuclear can be a good candidate, especially for the green hydrogen production. The clean drinking water for desalination purpose, and most important, it is also an energy driver having a very good load following characteristics. Sorry. Where are we and what we target to be till 2050? Today in India, if you look at, we have 22 units operating, 6,780 megawatt electric is producing, 9 units under construction, projects approved 12 units. Together, everything, if we add, something like 43 units may produce 22 gigawatt of electric by 2031. And many are in plan, and everything, if it comes through, by mid of this century, 2050, 66 units is a big number, but they will produce almost 50 gigawatt electric. If I convert to energy with a very good capacity factor, it's only 400 terawatt hour per year. And what we are talking about, 20,000 terawatt hour per year or 50,000 terawatt hour per year. So 400 vis this number is today negligibly small. And to meet the base load requirement, especially when coal is not available in the electricity grid, it's well known there should be a stable electricity in the grid, which should be something like 30 to 40% of the total energy. And rest 60 to 70% can come from renewables. And 30 to 40% of that number is a huge number. It's almost 8,000 to 20,000 terawatt hour in a carbon-free energy supply, and which is roughly 20 to 50 times of the projected electricity production by 2050 from nuclear. We are talking about 50 gigawatt. To me, it is too small. Unless the country targets 1,000 gigawatt to 2,500 gigawatt by 2050 from nuclear, the base load in electricity has to again be thought coming from coal. So what is the solution? Let us look at the constraints with the current nuclear technology. The most important for India is acquiring several sites. The right graph will show you what is our population density as compared to even the other countries like China, US, France, and India. We are growing, and we have the highest population dense country in the world. And the nuclear energy requires several zones. Exclusion zone 1 kilometer, emergency planning zone 16 kilometer radius, radiation surveillance zone 30 kilometer radius to meet those criteria of nuclear power plants. And if you keep so many zones one after the other, where is the site available to us is a big question. The MIT study says that today is one of the biggest question or biggest constraint for nuclear expansion is the large project cost and construction delays. Because a large size plant, the investment is huge. For example, you build a 1,000 megawatt plant. Today, you require something like 20,000 crores for building one plant. And because of the significant on-site work and civil construction delays, then the construction period is huge. It roughly takes 7 to 10 years to construct a plant. Then the 20,000 crore what we invest today, one has to wait something like a long time to start getting the return. And because of the non-modularity in design, there are issues in delay in supply chain, which affects the whole construction period. And all these affect the interest during construction, which is a significant factor as compared to total capital cost of the plant. Safety issue of the current reactors, I see today excellent, but very low probable core melt accident can occur, may occur. And that requires core melt mitigation strategy like core catchers, hydrogen mitigation devices, containment venting, and so on and so on. These layers we keep on putting for the safety barriers, which adds complexity, cost, and also the public fear against nuclear power. Then difficult to satisfy the no emergency planning in public domain, and that requires, if you look at the regulatory guide, the public evacuation, which is really a bad test and a bad experience, especially after Fukushima. So is the SMR bringing a solution? So that's why let's look at SMR. What is SMR? SMR is basically small modular reactors. These are advanced reactors having power capacity from 10 to 300 megawatt size as per the IEA definition, and they are targeted, specially targeted to produce low carbon electricity, base load driver for electricity supply when the grid is supplied by green energy in place of coal, load follower, hydrogen production, desalination, district heating, electricity supply to remote locations, defense applications, and so on. They are small because it produces a fraction of size of conventional large-size nuclear power plants. Modular because all the components and systems are to be factory built and assembled like a single product, and they can be transported to the site for direct installation. So that is very important when I say the modularity in design and construction. Reactor, they still use nuclear fission for energy conversion. Believe it or not, in the beginning, there were only small reactors. So small reactors historically have existed till 1970. The scale-up was there. The large reactors were designed especially to get the economies of scale. So small is not new. And if you look at the history of nuclear reactors, the water-cooled reactors were the first one where there is enough experience. To me, the water-cooled small modular reactors are the low-hanging fruits which worldwide have been targeting to deploy. And the major milestone in SMR technology was achieved with the deployment of KLT-40, the Russia's academic Lomonosov, the world's first floating nuclear plant that began commercial operation in May last year, producing 2 units of 35 megawatt each. So this made the history in the development of small modular reactors. 3 small modular reactors are in advanced stage of deployment. The CARAM is under construction. The NuScale, that is the American one, in the advanced stage of licensing. The SMART, the Korean one, is almost licensed. The Korea has joined hand with the UAE for deployment of the SMART. CARAM is in advanced stage of commission. I don't say commissioning, but almost they're towards commissioning. The first approach of criticality they proposed this year is almost 30 megawatt electric plant in Argentina. NuScale, the US, I'll say that, is designing, which is now planned to be built by several countries in Europe, as well as some of the Asian countries, as well as that in the United States. Many others also are under construction, in a high level of development. The Westinghouse has almost completed the design of 335 megawatt electric small modular reactor, and this is led by Westinghouse, and many of these components or safety systems are being tested by many, I will say that, by a consortium led by Italy. The Westinghouse SMR is another one. It's called 225 megawatt electric, 800 megawatt thermal. That is also in, they have completed the basic design. The mPower, which is from the Babcock and Wilcox of United States, they have also completed basic design of a 200 megawatt electric plant. The ABB, they have also completed 9 megawatt, which is a smaller one, of course, a 38 megawatt thermal plant. And there are 70 such designs which are being pursued, and some are in the advanced stages of design. Some have completed the basic design, and some have also approached the regulators for licensing. I'm not going to speak each one because of the lack of time. So broadly, if you look at water-cooled SMRs, there are 2 types. One is the block type SMRs, the left one, in which the steam generators, the pumps, they are joined directly on pressurizers. Directly, they are welded to the reactor pressure vessel. So the piping work here is almost eliminated. So they are joining neck to neck. The right one is the integral small modular reactors, in which all the components of the reactor, like steam generator, pumps, pressurizer, are positioned inside the pressure vessel like a single unit. So these are the 2 variants which the world is pursuing. The advantages of the integral reactor over the block type, that everything is inside the reactor. So there is no question of loss of coolant accident. So the safety-wise, the right one, that the integral reactors are much more safe as compared to the left one. So how the SMRs address the issues of current nuclear technology. The most important, especially if you look at India, getting the no sites with no emergency planning zone requirement, because it's requiring a huge 16-kilometer radius. These reactors, I'd say that the small modular reactors, they carry almost zero risk to the public. They're designed with a trademark of no impact in public domain. How it is achieved? The reactor is very small, below 300 megawatt. A radioactivity inventory is small. So release at the plant boundary never exceeds allowable dose limit under any circumstances. And that is why the public evacuation is almost eliminated by design. So it is what is termed as walk away safe reactor, in the sense, in case of an accident, the operator even can walk away, leaving the reactor to be safe on its own. In this regard, we have done a couple of calculations. I'll show you. If the reactor size is 100 megawatt electric, then what we have found out, if even in case of any extreme accident, extreme event, the fuel pins are dry, no water is available inside the reactor pressure vessel, it can be cooled by air itself and ultimately cooled by the containment, which is also indefinitely cooled by air, by passive means. Even for a 100 megawatt electric size plant, the clad's temperature never exceeds 750 degrees Celsius. If it is a 125 megawatt electric plant, it's hardly 825 degrees Celsius, and so on. That means if the plant size is below 100 megawatt electric, in case the fuel pins also dry, we can still cool it by passive means externally by air without exceeding the clad temperature above 750 degrees Celsius. That means even there is no question of hydrogen production for such extreme event, forget about core melt. Similar things also we did calculations. Suppose we have a heavy water reactor based small modular reactor. If the channel power is below 6 megawatt, similar situation also we found that the pin temperatures never exceed 800 degrees Celsius. So that is why, since the pin temperatures are so low, they don't require an emergency planning zone. So because of this, they have the superiority over Gen 3 and Gen 3 plus reactors. Gen 3 plus reactors also use some passive systems in their design. However, if you do a accident simulation under certain conditions, there is a possibility of clad temperature exceeding beyond limits, which leads to hydrogen production, some cases core meltdown. So these are the issues. On the contrary, SMRs being small, and if it is an integral reactor with passive systems in place, the clad temperature never will exceed the permissible limit. So it is extremely safe. Next is how early we can induct the small modular reactors. Technology for water-cooled reactors is matured, more than 6 decades old. Passive systems, several, I will say that, especially for ASWR, we have spent no less than 2 to 3 decades. And this technology has been developed, demonstrated. So this can be well leveraged without wasting time in R&D. Modularity in design, because as I said, major components of the reactor coolant system, steam supply system, they can be manufactured in centralized manufacturing facilities and integrated them as a single unit like here. If you look at the left one is a single reactor, which I say is integral small modular reactor. And the right one is a conventional PWR. For example, you can see the reactor pressure vessel at the bottom, at the center, the pressurizer, steam generator, the pump hanging left and right. But in the integral small modular reactor, everything is put inside a single pressure vessel. So from the factory, it comes as a single unit or a single product. And this can be transported from the plant, from the factory to the site for direct installation. So the work at the site is very, very minimum. Economic competitiveness, this is a major thing which is being argued worldwide. It's not a new thing here also, but there are a lot of studies also have been done. This is what I'm going to speak about here. SMRs differ from conventional reactors in many ways, which actually decrease the overnight cost, especially looking at modularization, factory fabrication, multiple units at a single site. So it is basically the economy of numbers versus size, which is the game. And the other advantage is lesser investment with early returns. A 100 megawatt plant, suppose, is cost 2,000 crore, vis-a-vis a larger plant which costs 20,000 crore. A small investor can put his money in a small plant. And if he knows that in 2 to 3 years, he is able to produce electricity and sell it, so the return is early. So many investors will be tempted to invest in the small reactors, and that will cause a large expansion in nuclear power program. And because you are trying to produce electricity in a small period, the construction delays are much, much smaller. So the interest during construction is much less than large reactors. So the OECD exercise shows that how the capacity of the reactor reduces the cost. The left side, the bottommost axis shows the reactor size, the right side, the right axis shows the cost. And this is true if the small plant is just a daughter of the large size plant. But in SMRs, we are not talking to the same. The SMRs design is almost different to that of the large size reactors, especially the fuel design can be same. Otherwise, the steam generators, the pressure vessels, the pressurizer, even some don't have the pumps. They're all installed inside the reactor itself. The reactor containment is much, much smaller with steel containment, which takes much lesser time to build, and so on and so forth. So it is, this SMR is not a daughter product of a large size reactor. They're completely different. So we cannot compare the power ratios of the cost of a large reactor to be put that for SMR. And there are many, I would say that many experts have done these calculations that the fast, the fork, that is the fast of a kind to a nth of a kind, how the cost reduces. And suppose we compare a 8 megawatt electric large size reactor, the first one to the last one, similarly 150 megawatt smaller modular reactor, first one to nth one could be 8th or 10th one, then the reduction cost is almost in the same ratio. It is achieved. And the qualifying cost, this is also by several experts who have done this, that if the factory fabrication comes into picture, the cost reduces by almost 30%. And the learning, that is from first unit to the, I would say, 8th or 10th unit, will further cost reduction in the cost by another 20%. 10%, suppose we go for multiple units at site, and early power another 4%, and so on and so on. And if you look at the large size reactor versus a small size reactor, the cost can be reduced to several times because of this. And the recent US study shows that the levelized cost of electricity for 4 into 150 units of SMRs could be something like 5.3 rupees per unit for the first of a kind plant, and it could be close to 4.6 rupees per unit for the nth plant. So it is not much different. Next part, what are we going to speak about? The load following for the small modular reactor. Load following is a very, very important aspect, especially when the grid is going to be supplied by electricity from renewables. The grid is going to fluctuate a lot. In a thermal power plant, the base load we are driving, and in thermal power plant also, it is easy to maneuver the load following by changing the amount of coal or gas as the fuel. We can change it depending on the demand, which is not possible in the nuclear power plant so easily. it can change over a small thing. However, in a small modular reactors, the load following characteristics can be easily achieved by switching the number of reactors to the grid as per the demand, and rest can be coupled for electrolysis, for hydrogen production, or for desalination, depending on whatever the demand comes. Make in India, large employment generation, all components of this reactor can be manufactured in India. So several hundreds of such reactors if we build will not only boom India's manufacturing sector, service sector, but also help in reducing unemployment. Most important, this is what I was trying to speak about, how SMRs can fit in the retired coal plants. The bottommost graph shows year-wise how the coal plants are going to retire. This is our projection. We consider the design life of the plant, coal-based plant is 30 years, assuming they don't get extension, especially when we go for the non-carbon energy sector. So our projection is that by 2050, most of the existing coal plants will be retiring, almost 200 gigawatt electric. And the right one shows the rate at which they are going to retire. If you look at the year-wise capacity addition of coal plants with their size, till I will say that most of these coal plants, they were really small size, less than 300 megawatt electric size. A few, I will say that only few, and which has been added very recently were large size plants. Otherwise, historically, only small size plants, 250 megawatt electric or so, they were all there in the thermal power plants. Look at where they are located. Most of these thermal power plants are located in the place where the coal is available, especially in the Central Asia, Central India. And if you look at the seismic locations, they're mostly located in Zone 2 and very few are in Zone 3. So which really qualify mostly to be replaced by nuclear power plants. This I took a history from the Central Electric Authority, and it shows that almost 84 gigawatt electric coal plants have retired by 2020. Now let's look at a comparison. What I have done, taken a site in UP in one of the thermal power plant. It produces 3,760 megawatt electric. It's a huge plant, basically. There are several thermal power plants in this area. They occupy 10 kilometer square area without ash pond and 23 kilometer square area with ash pond. Suppose we go by our conventional nuclear power plant, 2 into 540 megawatt electric, they will occupy 0.8 kilometer square area, including reactor building, turbine building, and so on. That is almost 0.182 acres per megawatt. And with 3 kilometer square, if we consider exclusion zone, look at 3 kilometer square, vis-a-vis almost 33 kilometer square, which this thermal power plant was requiring. Now, let us say we give this, I'll say that 23 kilometer square for solar or wind, maximum they can produce 720 megawatt electric as compared to what the solar was, the thermal power plant was producing more than 3,700 megawatt electric. We tried to fit in with the footprints of this small modular reactors in that field, and what we found that while keeping the exclusion zone of 1 kilometer radius, we can safely put 32 numbers, which comes to be about 3,200 megawatt electricity capacity can be installed at site of 3,760 megawatt electric plant while satisfying the exclusion zone criteria. If we go with solar and nuclear, with the 23 kilometer square ash pond, suppose we put the solar, they will yield additional 730 megawatt electric. So total we can produce 3,930 megawatt electricity as compared to 3,760 megawatt coal plant. Hence, to reduce hence to replace the retired coal plants by SMR, what do we say? The exclusion zone criteria can still be maintained as per the ARV. For safety, these small modular reactors don't need an exclusion zone, but for nuclear security, they will be definitely requiring that 1 kilometer exclusion zone. EPZ, it don't require because of this requirement of, because of their qualification of no core degradation or hydrogen production. So integral PWRs or HWRs of 100 megawatts electric are safe enough to meet this criteria. NIAS BRC has conducted some studies I'll show you here. Very recently, it was presented during our joint meeting. These were the projects supported by BRNS. So if you look at the Talcher Thermal Power Station, this is already abandoned this place. Earlier, this site was producing 460 megawatt. And if we put these small modular reactors in the same site, while fulfilling the exclusion zone criteria, 600 megawatt can be easily produced. In the Guru Gobind Ropur Thermal Power Station, this site was producing 1260 megawatt, and the NIAS has put our SMR footprints here in the same region. It can qualify to produce 14,800 megawatt. Several, I'll say that it's almost 12 times what it was producing. The Parakat TPS, that is thermal power station, it was producing 2,100 megawatt. If we put the small modular reactors in that place, it can produce 2,000 megawatt, almost the same what it was producing. So roughly what I would say that this exercise is going on. I think in, I'll say few months we'll come out with a full NTPC site, how many or what, I'll say that what amount of the thermal power can be replaced by small modular reactors. The other targets of the SMRs is the green hydrogen production. Typically per megawatt electrics, around 480 kg of hydrogen can be generated per day using low temperature electrolysis. Suppose we go to high temperature steam electrolysis, almost 630 can be generated per day per megawatt electric, but that requires high temperature reactors. So SMRs, apart from electricity production, can be utilized for green hydrogen production. This is another important slide I wanted to show you, that how desalination is going to be one of the important attributes apart from the electricity production or energy crisis. This is something the country is going to see very soon about the water crisis. Look at the topmost table. In 1951, our per capita water availability was 5,177 meter cube per year. The rain god gives the same amount of water, but population keeps on rising. By 2050, suppose we are 164 crore, then our per capita water availability will be 1,140 only meter cube per year. Then it will be in the water stressed region as per the UN classification. In that case, desalination will be very important for supplying clean drinking water. And typically per megawatt electricity, 6,000 meter cube per day clean water can be produced by SMRs. This is my last but one slide. I will say that non-carbon energy sector has given us plenty of opportunities. We say challenges, but it is plenty of opportunities. How? Let us look at the pre-industrial area. Or this slide I have, I beg apology. This slide I have taken from our late Dr. Sri Kumar Banerjee sir. He was former chairman Atomic Energy Commission. I took this slide from him once he was presenting post-Fukushima in a energy forum. So somehow I like this slide, so I'm showing it here. What he says that several thousands of years ago, the human was living in forest with animals and birds. Once there was fire in the forest, the animals and birds flew away, but humans felt the heat and they utilized the heat And that's how the civilization started. And that is why today we have come to this level. So nuclear has a lot of potential. It's nothing to fear, but utilize this energy. But then, how we are going to utilize it? And if you look at history of our science technology, before 1950 or 1947, our science and technology was not at par with that of the Western world. But today, we are competing well enough with that of the Western world. So it is only the industry which has to groom enough or which has to be engineered enough to take up these small modular reactors. Then I will believe that if 200 gigawatt plus can be produced from these small modular reactors in the next 30 years in the vacated coal plant, probably it will be one of the definitely a strong candidate to meet the base load in absence of coal. And that gives plenty of opportunities to Indian scientists, technologists, as well as the industry. So with this, I thank you. I thank you all. Thank you, SBNI, for giving me this chance to speak to all of you. And I also beg apology if I have done mistake, because there are many of these slides I have taken from literature. Numbers could be differing from here and there. So I also beg apology if somewhere I have done mistake. Thank you again. Thanks a lot.
So thank you, Dr. Nayak. It is like almost like two colloquia back to back. Without much more spending any more time, I would like to see if there are any questions from WebEx as well as YouTube audience. Why is average plant load factor is as low as 53%? I think even break-even CF, I don't know what is CF, is 68% in ECEA.
Capacity factor.
Is ECEA. What should we do to improve it to say 80% or more?
This number is because of, what is the electricity driver in the grid. So today the electricity driver in the grid is from coal-based sources, of course. And also the energy driver is also substantial. I don't say substantial, but quite a good amount is from renewables. Nuclear segment is very poor. So the average plant load factor, which CA has shown in their report, is almost 53%. So how to increase to 80% or more? Yeah, so that is what I will say that nuclear has to play a major role, and in the decarbon energy sector, then only the capacity factor is going to be increased. So I don't have any answer to that, why the thermal power plants have a poor plant load factor.
And then he added some more points. Smaller the size of core, greater would be the need for enrichment.
Okay. So I think if you look at this part, it has been addressed by reactor physicists. Small size, it doesn't mean that it is a 10 megawatt or 20 megawatt, 30 megawatt. The competing core size is something like 300, 350 megawatt. And the fuel utilization has been also compared, especially the burn-off levels for PWRs with 4-5% enrichment with that, and the life of the core is very, very comparable with a 1,000 megawatt plant. Okay, relatively, there is a slightly more enrichment, but the fuel utilization cost or the fuel cost, as you know, is not so significant with regard to the cost of the electricity. It is slightly more. So this part I agree, but it is not so significant. Then the second thing is, apart from exclusion zone of 1 kilometer radius,
the other
zones can support population to live there. Yeah. So exclusion zone, actually the small modular reactors, if you look at their safety calculation, they're so safe enough, they don't require even exclusion zone. But the nuclear security will require, definitely, some zones where public, I will say that, is not allowed to move. Outside the exclusion zone, definitely the public should be allowed to habitate. And that will definitely increase the confidence also of the public to nuclear power. This is very, very important. Maintenance issues in pumps, valves, etc. in the integral SMR design. The pumps are located outside the reactor. The pumps, many don't keep inside. And some of the SMRs are designed without the pumps, that is natural circulation core cooling, because the size is small, so they don't require the pumps. Valves are external, so they don't have these special issues. I hope I addressed Sanand Kumar Saab, your question to some extent.
Thank you. Any further questions? I think there are some more questions on the chat box of YouTube. What will be the status of spent fuel and its safety issues in SMR?
Okay, I think spent fuel and status of, I'll say that safety issues. See, SMR means we are not targeting one site, 100 megawatt plant. I think this is something is wrongly understood. I showed some sites, especially in the retired coal plants, where you can put 30 numbers, 40 numbers, 50 numbers, depending on how much it can accommodate. So the spent fuel bay can be common to a site. A site can have a common spent fuel pool, and then the safety issues of this spent fuel will be similar to that of a conventional reactor. So it is not a different one. So I don't think that this is something one has to worry about, that safety issues of the spent fuel is something different from that of the large reactors.
Any further? Any questions on the WebEx platform directly? If there are no further questions, we can finally thank Dr. Nayak once again for an excellent marathon kind of a talk. Thank you very much, Dr. Nayak.
Thank you, sir. Any comments, sir? Kakolkar sir, Grover sir, any comments from your side?
Go ahead, Dr. Grover.
Okay. Let me make one comment. There was a question regarding low capacity factor of 53%. These capacity factors in coal-fired plant, if you go 4 or 5 years back, they used to be very high. And gradually, as the renewables have been added to the grid, capacity factors have come down. The reason being that during the daytime, when solar is available, coal plants are asked to back down. Because the coal plants earlier, they have the capability to work at higher capacity factor, but now coal plants are working at as low as 55% capacity factor to accommodate solar plants. What actually has happened in India, that renewables have been added without doing a total system analysis. So coal capacity is enough to meet the peak load. Even if we had not invested anything in renewables, coal plants would have met the capacity. But that would have been environmentally problematical. It would have meant more carbon emissions. So addition of solar have reduced carbon emission, but it has come at a cost. And the cost is that coal plants are working at low capacity factors. And the result is health of the entire sector economically has been very badly affected. So this, I thought I'll just give the answer to that question, that why plants are operating at low capacity factors. And this is very well documented. Data is available on the website of CEA and Ministry of Power in this regard. As otherwise, yes, SMRs are a way to go. I remember as long back as late 80s or early 90s, there was a paper by L.S. Tong where he has plotted reactor size versus peak temperature. And what Dr. Nayak has tried to say today, that in case reactor size is 100 megawatt, the peak temperature, fuel temperature will not go beyond 700 degrees centigrade. This has been well known, but now it has again come to the fore, and one can really proceed further on those lines. And another point which I want to add is that some companies are advocating use of PSWRs as small and modular reactor. We can modularize the design. This is the claim which they have made. Come up with a 300 megawatt PSWR, and that is a technology which will be easiest for us to proceed further because we know every aspect of PSWR technology. So I'll just end with these comments, and over to you, Dr. Kakotkar. Maybe you want to add something.
Yeah, of course. Let me add some different points. What you said is exactly right. But before I begin, Dr. Nayak, I think your arguments have to be a little more aggressive. In the sense, we should first ask a question: does India want to be a developed country or not? And what is the meaning of developed country? Developed country where quality of life of our people is comparable with the best in the world, the so-called developed countries. Now, if you want a human development index of 0.9, that is what would be required, then the correlation that you showed, that itself will tell you that you need that 2,400 kilogram oil equivalent or corresponding kilowatt hour per capita equivalent. And then actually it will go to your high estimate, the 50,000 terawatt hours. Now, so if you decide to settle for 20,000 terawatt hours, the business as usual, as you are saying, which would correspondingly mean that we will settle at a lower human development index, maybe 0.8, 0.75, something of that kind. And recognize there is a big scatter. We can reach a higher human development index even with somewhat lower. But if we don't do things well, it may be the other way. Even if you spend so much of or get so much of energy, the quality of life may still not be good enough, as has happened in many countries. So the short point is, I find everybody in our country, they find it very hard to even say that we need so much of energy. And my question is, if you peg your ambition to a lower number, recognize that you are reconciling that for all time to come in the history, you will be remain underdeveloped. See, the point is with net zero, this is what is the new challenge. Earlier, it was that you could pump in more coal, more oil, more gas, produce more energy, and the question is when we will reach developed status. It may take a long time, but we will reach there. Now with net zero, as you yourself said, the clean energy which is available is so limited. So the only addition to energy can come from nuclear, because renewable energy have accounted for everything. And if the ambition of nuclear is not good enough, then you have to actually reconcile to the fact that India will remain underdeveloped. So that's the point I wanted to flag. That is number one. Number two is Dr. Nayak may be perhaps aware, in Japan, where were you? Tokyo University?
Tokyo, I said, Tokyo Institute of Technology.
Yeah, so Professor Sekimoto was there, right? No, you may not be knowing. But
I know him.
you know
My
him.
examiner.
Acha, right. So he, I think in 70s, he wrote a paper essentially looking at what determines the cost of nuclear reactor, whether it is the criticality constraint or a power constraint. And then he says that once you go to reasonable size, then criticality is no longer a cost determining factor, which it is in case of research reactors, for example. But when you go higher, it is the safety systems that add to the specific capital cost. And he actually proved that 100 megawatt is the right size where the cost per megawatt can be in principle brought to a minimum. Now, recognize this was done way back in 1970s, things have changed there. But not only the lesser capital cost because the size is small, but even specific capital cost, if the reactors are engineered cleverly, can actually go through a minimum. Now it may be 100 megawatt, it may be 200, 300, but it will be something of that kind. And this is something, basically we are trying to economize because of the scale effect, economy of scale. The small modular reactor, the argument is economy of volume. Now, economy of volume requires that you will get orders for mass production in the factory, like the aircrafts are being made. Now, that requires a national level planning, and the orders must flow. For example, depending on the capacity, maybe 10 reactors a year or 20 reactors a year, that kind of orders must flow. Then you really recognize or achieve the economy of volume, and the cost will really come down. There is a strong merit in doing so. So those are the 2 points, but it's excellent, I think, wonderful presentation. And only thing is, I don't want people to carry the notion that India, we should get into SMR as a mainstream product for India's power capacity addition, because our requirements are large. So I think our workhorse should still remain 700 megawatt, but surely we should add a parallel stream and be very aggressive about it in terms of the SMR as a product. That should be the route to go further. But excellent presentation. Thank you.
Thank you, sir. Thank you very much.
Thank you.
Thank you, sir.
Let's.
Okay, sir. Namaskar, sir.